All right, so we have started talking about important bonds in biological molecules, and by bonds, we mean the things that hold atoms together so that they can form larger structures. And I said that there were three kinds: hydrogen bonds, ionic bonds, and covalent bonds, and that the weakest kind of bond are hydrogen bonds, then ionic bonds, and the strongest bonds are covalent bonds. And we also use the analogy that there are different ways of joining pieces of fabric together to make clothing, and that covalent bonds are like seams in your jeans, maybe the double sewn seams, really strong, going to stay together. That the ionic bonds, pretty strong, stay together pretty good, so they're like the buttons in the button fly of a pair of jeans. Whereas hydrogen bonds, each individual hydrogen bond is super weak. So it's like one little hook and thread in some Velcro. Each one of them super weak, but in Velcro, there are hundreds, I don't know, maybe thousands of those individual bonds. Hydrogen bonds in biological systems are each individually weak, but there are many of them. Right? So we were starting here, and then we were going into a little more detail about covalent bonds. And we learned that covalent bonds are the sharing of a pair of electrons. So in covalent bonds, I will say, oh, I have got one electron, and oh, I wish I had a second electron. Then I'd have a full outer electron shell. And you're saying the same thing. And so I said, hey, how about this? I'll share mine with you if you'll share yours with me. And then together we share a pair of electrons. I guess my phone just became an electron, right? So that's a covalent bond, and that's the strongest kind of bond. And as an example of a covalent bond, we showed the bond between two hydrogen atoms. Remember that hydrogen, it's got an atomic number of 1. So since it does, it has one proton. When it has no charge, it has one electron. But its outer electron shell, well, its only electron shell, could technically hold 2 electrons. So each one of these hydrogen atoms is busy saying to itself, oh, I wish I just had one more electron. Then I'd have a full outer electron shell. And they meet up with each other and they go, hey, I'll share my electron with you if you'll share your electron with me. And when they do, you end up with a hydrogen molecule that's put together by a covalent bond. Now, the covalent bond between hydrogens in a hydrogen molecule is a non-polar covalent bond. This one is an example of non-polar. Okay. We call it non-polar when the two atoms are playing fair and they said, I'm going to share my electron with you. And so they are evenly sharing that pair of electrons. That's non-polar. But there actually is another type of covalent bond. The non-polar type is when there's even-steven sharing of the pair of electrons. The polar type is when one of those atoms is cheating and it's keeping that pair of electrons for more than half the time. So I think I use the analogy that covalent bonds are sort of like if you can't afford a BMW and your friend can't afford a BMW, so you go together and you buy a BMW. Is it as good as having your own BMW? No, but it's better than not having a car, right? So in that situation, if you and your friend were sharing it evenly, like I get it this week, you get it next week, I get it the week after that, that would be a non-polar covalent bond. Or maybe I get it Monday, you get it Tuesday, I get it Wednesday, you get it Thursday, I get it Friday, you get it Saturday, I get it Sunday, you get it Monday. That would be non-polar. But a polar covalent bond would be when one of you is cheating. So what if you got it Monday, Tuesday, Wednesday, and your friend got it Thursday, Friday, Saturday, Sunday? You'd be like, not fair. That's what a polar covalent bond is. So one way to remember it is in a polar covalent bond, one of those atoms is pulling the electrons towards it for more than half the time. So polar has a puller. One of those atoms is cheating. Now, in a polar covalent bond, whichever atom is hanging on to those electrons for more than half the time is going to be slightly negatively charged. And in a polar covalent bond, the one that doesn't get 50% of the time, it has less than half the time, it will end up being slightly positively charged, right? Polar covalent bonds are necessary for the formation of hydrogen bonds, and we will be talking about that in a little bit. Before we talk about that, let's talk about ionic bonds, all right? In ionic bonds, no one is sharing a pair of electrons, okay? In an ionic bond, one atom has decided, you know, if I just get rid of an electron, if I just totally decide, hey, this particular electron, it's out there by itself. In the case of sodium, I'm never going to get 7 more electrons out there. I'm just going to give it away. If I give it away, look, I've got a full outer electron shell. And then there will be another atom, like chlorine in this situation. Chlorine says to itself, man, I just need 1 more electron and I've got a full outer electron shell. If only someone would give me their electron. So if these two guys come close together, sodium wants to give it away, chlorine wants to pick up an extra one, then afterwards you can see, oh look, both of them have full outer electron shells. I'm sorry, something's wrong with this picture. Those 2 electrons should be in this electron shell. I'll try to fix that. So both of them have got full outer electron shells, so that's one way that they're happy. But what has changed? When sodium gave away one of its electrons, it now became positively charged. It became a sodium ion. Why? Because sodium has got 8, 10, 11 protons, so it needs 11 electrons, and right now it only has 10, right? Chloride is a negatively charged ion because it has 1 extra electron. And so now they're oppositely charged, and just like in Hollywood, opposites attract. And so those positively charged sodium ion is attracted to the negatively charged chloride ion, and they're bonded to each other. Not as strongly as in a covalent bond, but pretty strongly. And this is a good example of an ionic bond. Right? So here we see this happening in real life. The sodium says to itself, right now, wait, the sodium says, oh, if only I didn't have that 1 electron, I'll give it away. In this case, the sodium gave it to fluorine, and the sodium becomes a positively charged ion. The fluorine becomes a negatively charged ion. And now they are oppositely charged, and opposites attract, so they are joined together by an ionic bond. So how is this different from a covalent bond? It's only 1 electron, and they're not sharing it. There's 1 atom that literally has given away an electron. The one that gave away the electron, in this case sodium, now has become a positively charged ion. The one that received it, it's got an extra electron, has become a negatively charged ion, and they are attracted to each other, kind of like magnets clicking together, right? So that's an ionic bond. Now, let's talk about hydrogen bonds. Hydrogen bonds are found joining together, I'm trying to make this come back. Okay, not coming back. Hydrogen bonds are found very abundantly joining together adjacent water molecules. Now, let me be clear about this. An individual water molecule itself is actually put together by polar covalent bonds. Okay, so each one of these white atoms is a hydrogen, and the red atom is an oxygen, and they are joining in a polar covalent bond. And oxygen, being a really big atom, it is hanging on to those pairs of electrons for more than its fair share of the time. Not fair. What is hydrogen going to do about it? Hydrogen's a little tiny atom. So on this particular molecule, this water molecule, the oxygen end is slightly negatively charged, and the hydrogen ends are slightly positively charged. Now, they're not ions, so it's not a full plus or a full minus, it's a partial plus and a partial minus. Now, this weak positive charge at the end of each hydrogen is attracted very weakly to the negative charge at the oxygen end of the adjacent water molecule. And so they're joined together by hydrogen bonds. Now, the hydrogen bonds are very, very, very weak, but in water, there are so many of them that it actually makes water behave in ways that very few fluids do behave. Water forms droplets, very large droplets, very, very well, because water likes to stick together. And also, if you put heat energy into water, water does not change in temperature very quickly when heat energy is added, and that is because of the breaking and forming of those hydrogen bonds. You know, a place where you should know for the first exam that hydrogen bonds are super important is holding together the two sides of DNA. Here we've got a little teeny tiny segment of DNA. I'm always showing these images of DNA, and very often I forget to tell people this is not a DNA molecule. This is a little tiny bit of a DNA molecule. What do I mean by that? Each one of these blue sort of walking areas here, like that one right there. Okay, I don't know what happened. I'm going to make it yellow. Okay, each one of these things is one base pair, right? So if we were to count here, I don't know, I'd be guessing maybe there's 30 base pairs right there. In one of your molecules of DNA, there are 50 million base pairs. So when I tell you that this is not DNA, this is a little teeny tiny segment of DNA, I mean a little teeny tiny segment. This is less than 1/1,000,000th of a strand of DNA. But DNA is a super important molecule in living things. And this DNA is actually made out of two different strings of DNA, right? So let me draw again. So out of this DNA, this is one string of DNA, all right? And let me change my pen color. I'm going to make it orange, okay? That didn't work at all, did it? What did I do? This is the other string of DNA, right? DNA is made out of two strings that are wrapped around each other. And keeping your DNA in good shape is a super important job for your cell to do. And the two strings of DNA are held together in the center by hydrogen bonds. And like Velcro, each one of them is super weak, but there are 50 million of them. So it holds the DNA together very strong. Now, we use hydrogen bonds there. Why don't we just put a seam there? Why don't we just put a covalent bond holding the DNA together? Well, why is it that you might have Velcro in some part of like maybe your athletic pants. You put Velcro where you're going to want to open it and close it frequently. DNA, in order to do its job, parts of it get opened and then closed again. And so we put hydrogen bonds there, just like you would put Velcro in places where you wanted to be able to open and close an area of clothing, right? We will start here at the beginning of the next video.